Thank you very much to the organizer for giving me this opportunity to talk about this work that we carried out at Gran Sasso Science Institute about the early X-ray emission of shock gamma burst. So our paper is out on arXiv today. So if you want to take a look at it, you can scan this QR code. So let me start with a very brief introduction on gamma burst, since Pawan already did that. So these are extragalactic MEV transients that are powered by collimated ultra-relativistic jets. So they are characterized by two main emission episodes. The first one is the prompt emission phase, which typically peaks in the gamma ray energy range, is highly variable and short-lasting, from a fraction of seconds to several minutes. This is produced by the internal dissipation of the jet kinetic energy. Later on, the jet interacts with the circumverse medium, producing a shock where particles are accelerated and radiates via synchrotron and inverse Compton losses. This produces the afterglow radiation, which is long-lasting and visible through all the electromagnetic spectrum. So according to the bimodal distribution of the duration and the hardness of the prompt emission spectrum, the GRBs are divided into two classes. We have short hard gamma ray bursts that are associated with binary neutron star mergers, and long soft gamma ray bursts, which last more than 2 seconds and are associated with the death of massive stars. And the joint detection of a gravitational wave signal and a short gamma ray burst from a binary neutron star merger in 2017 confirmed that merger-driven gamma ray bursts are very promising multi-messenger sources. And in multi-messenger astronomy, a crucial point is to achieve a very rapid and accurate sky localization of the event to enable the electromagnetic follow-up with narrow field instruments, such as ground-based optical and infrared telescopes. The gamma ray satellites are very well suited for transient detection, since they are all sky monitors, but they have a relatively poor localization of 10-100 square degrees. X-ray satellites instead can give an arc-minute localization of the event, and this is the reason why it's very important to detect the early X-ray emission of such events. So far, the most precise satellite to detect a localized gamma ray burst was the SWIFT mission, which was launched more than 20 years ago. So SWIFT is equipped with two X-ray instruments. We have the Burst Alert Telescope, which is sensitive in the hard X-ray and has a wide field of view and provides the GRB trigger. Then we have the X-ray telescope that is sensitive into the soft X-ray range and can detect, has a narrow field of view and can detect the X-ray emission after about 1 minute after the burst trigger. So SWIFT has very rapid and automatic ray point capabilities. But now we have a new instrument that is looking at a soft X-ray sky, that is Einstein probe, which employs a new technology called lobster eye optics to combine a wide field of view with an arc-minute localization, and is expected to detect the X-ray counterpart of many gamma ray bursts. So how do short GRBs look like in soft X-ray? After the hard and short prompt pulse, we have the so-called extended emission that is softer and lasts about 100 seconds. This emission then transitions in a so-called steep decay phase that is characterized by a rapid flux decline and a strong spectral evolution. In short GRBs, this has a time scale of around 1000 seconds. Then we have the onset of the afterglow. The late afterglow has been very well characterized by the group of Fong and collaborators. However, there is still the early X-ray emission of this burst remains still poorly characterized. But it's important to study and understand this radiation because it is considered as the tail of the prompt emission phase, and as such, it can offer insights into the jet physics and the emission mechanism happening in GRB jets that are still poorly understood. Also, this emission is brighter than the afterglow and is softer than the prompt emission phase. And so it's the ideal target to be detected and localized by the current wide field X-ray monitors, such as Einstein probe. And for all these reasons, we decided to systematically analyze the temporal and spectral evolution of the early X-ray emission of short gamma ray bursts. So we selected our sample starting from the SWIFT catalog, and we selected the GRBs which had the brightest emission in XRT because we needed enough statistics to perform a time-resolved spectral analysis. So here I'm showing the XRT light curve of the GRBs in our sample compared to the all the other short GRBs detected by SWIFT. And in our sample, we included short GRBs with extended emission, as well as two oddballs that are short GRBs with a prompt emission lasting a few tenths of seconds, but were associated with compact binary merger progenitors. So here, as an example, I'm showing the buttoned XRT light curves in blue and red of GRB 211211A that was one of such oddballs. In the lower panel, I'm showing the XRT hardness ratio, which is a proxy of the spectral evolution happening in this steep decay phase. So we use this quantity to decide the time window we wanted to analyze. And we performed for all the GRBs in our sample a time-resolved spectral analysis of both XRT and BAT data in the 0.3150 eV energy range. So here I'm showing our model. So we interpreted the flux evolution and the spectral evolution of the early X-ray emission as the cooling of a non-thermal spectrum, whose peak is transiting across the instrumental band. So this is an empirical model of this emission, and we tested two different spectral models, the synchrotron and the empirical multi-broken power law. So in our model, the spectrum doesn't change in shape, but its peak energy shifts to lower energy and the spectrum becomes progressively fainter. So here I'm showing our model of the evolution of the GRB 211211A spectrum with the time indicated with the color map. And here I'm showing the results of this analysis applied to all the GRBs in our sample. So on the right plot, I'm showing the evolution of the flux in the 0.3150 keV energy range, which can be considered as bolometric, as the peak almost always lies in the instrumental band. And we can see that this flux drops by 2 orders of magnitudes in 400 seconds. On the right plot, I'm showing the evolution of the synchrotron cooling frequency, and we can see that it drops by 1.5 order of magnitude in the same interval. Then we computed the intrinsic properties of the GRBs with measured redshift in our sample. So here I'm showing the rest frame synchrotron cooling frequency plotted as a function of the isotropic equivalent luminosity for all the bursts in our sample. And we can see that we discovered a tight correlation between these two quantities across all the GRBs in our sample. So we fitted these data points with a power law relation, finding a slope of about 0.6 and a very low scattering around this relation. Then we extrapolated the relation to higher energies, and we found that it can perfectly describe also the properties of the prompt emission of the short GRBs detected by Fermi GBM that are represented by the green points. So from this relation, we deduced that the prompt emission, the extended emission, and the steep decay in merger-driven gamma ray bursts should have a common origin. And this relation is also useful to identify GRBs that have compact merger progenitor and are long-lasting, such as 211211A. So a few words about the possible physical interpretation of the steep decay phase. One of the most used model to explain this emission is the so-called high latitude emission model. So according to this model, we see the steep decay phase when the prompt emission shuts off, and we start to see, as an observer, the photons coming from the line of sight, and then at later times, we see the photons that comes from larger angles. And the evolution of the X-ray light course is due to this model. But this model is not consistent with the slope of the observed relation that we find. There are two other possible explanations. One is the adiabatic cooling, according to which the particles that emit the prompt don't radiate efficiently, and so they undergo adiabatic cooling. And another possible explanation is that the X-ray steep declines follows the declining power of the central engine. So we also assessed the detectability of these events with the Einstein probe. So what I'm showing in this plot is the flux computed in the WXT energy range as a function of time. So the blue circle represents the prompt emission data points, while the blue curves represent the steep decay phase. The four different curves represent the WXT sensitivity curves computed for different photon indices, as we need to compare them, the prompt emission with the sensitivity curve that is computed for hard photon indices, and the steep decay phase has to be compared with the sensitivity curve computed for soft photon indices. So we can see that at redshift 0.1, both the emission are detectable, but the event rate is very low since the conmoving volume at this redshift is very small. And when we increase the redshift, the prompt emission phase starts to become undetectable, but we can still basically detect all the steep decay events. And at redshift 0.5, basically the prompt emission is not detectable anymore, while we can still catch the steep decay phase. We give also a very conservative estimated detection rate of 0.5 events per year. So what the message here is that in Einstein probe WXT, short gamma ray bursts will look like X-ray transient lasting few hundred seconds. So this is my summary. So in this work, we first characterize the temporal and the spectral evolution of the early X-ray emission of measure-driven GRB candidates. Also, we discovered a new peak energy luminosity relation at lower energies. And we also assessed the detectability of these events with EPWXT, and we understood that this event will look like X-ray transient lasting few hundred seconds in Einstein probe. So a follow-up is needed to better characterize and identify these events. So thank you very much.